Our next presentation is going to be from Ryan Boyd. Ryan is on our developer relations team and going to be talking about graph algorithms within the Neo4j product set. Take it away.
Thank you very much, Dave, and this mic. All right. Wow, everyone can hear me, and quite loud at that. Good for the afternoon to wake everyone up. Let me push this mic out of the way. So I'm here today to talk about graph algorithms, and just some context setting here. How many people have already used graph algorithms in Neo4j? Okay, handful, that's good. Ask them questions if you have any, and myself, of course. So how many of you have already used Neo4j, or how many have already used Neo4j? All right, so it's quite a bit. So we are going to actually have some code in this talk and some pretty graphics, and hopefully I can keep you all entertained without needing too much of that mid-afternoon coffee. So this talk is about Carpe data. Seize the data, make the best use of the data as possible. We invite you to do this so that you can get the most value out of your data. One of the big challenges we have as an industry right now is that there are countless exabytes of data that just goes collected and unused. So let's figure out how to bring value to that. Now, Neo4j originated as an OLTP database. It's an ACID-compliant database trusted to store your online transactional data. Subgraph queries are often performed, and actually the workload of a graph database typically is more towards the query side, with super high performance on these subgraph queries. And it gets that because of the native graph technology. It is native all the way down the stack, so you don't get the join bombs and things like that that you would be getting doing these types of relationship queries on other types of databases. But we're here to talk about analytics, not just OLTP. We need to analyze our data and data relationships in order to make good decisions, like these decisions. And how have people done that in the past with graph? This is nothing new. Graphs are a technology which has existed many years, and people have used this technology to analyze data. So Gephi is the original tool that many folks are using for analyzing graphs. It's a desktop-based Java application, heavily used in academia, and you can even use Gephi along with Neo4j. The APOC library, which is super useful if you guys haven't used it yet, use it. The APOC library allows you to stream data from Neo4j into Gephi to analyze that data client-side. Gephi was actually built by the same people who founded Linkurious years later, and the Linkurious visualization tool that many of you folks have probably heard of. iGraph is another way that people have analyzed data in the past. iGraph isn't a desktop tool, it is a library. It is a library that works with R, with Python, with C, and C++. It is single machine and often single threaded. But you can also use this along with the R library for Neo4j, R Neo4j, in order to access data from Neo4j and analyze it within your Python or R library or code. Well, R Neo4j if you're doing it in R, and then we have a Python library if you're doing it in Python. Spark is today's hit term. I imagine all of you know what Spark is. And Spark has an extension called GraphX, which is a distributed in-memory analytics solution for analyzing graphs. And you can also use this with Neo4j data. And you can also use the OpenCipher query language with a project that's kind of new and upcoming called CAPS, C-A-P-S, to query the data that is in Spark using the Cypher query language. So you can use this same query language regardless of whether your data is over in Neo4j or whether your data is in Spark, and then you can analyze it on Spark. So today, these have largely been separate. Online transactional processing and analytical processing have been two entirely disjointed nodes or disjointed single node graphs. And what we've had, though, is a communication layer between them over the network. So over the network, over sockets. There's been some work of trying to say, can these things run in the same memory space, so Neo4j and Spark in the same JVM? But largely, it's about transmitting data back and forth between these different systems. And if we jump back a few years, I actually gave a talk at Graph Connect in San Francisco, which basically said, do that. If you want to do whole graph queries, you should export the data over to Spark, run your analytics on it, and get the results, put them back into Neo4j, and use those for your real-time decisions. Times have changed. And part of that is because the technology space has changed. Part of that is because we've learned through these exercises that we can do something different. And part of that is that we realize that large scale doesn't always equal greater performance. Back when I worked on MapReduce and Hadoop projects when I was at Google, we had devs that would use MapReduce on data sets that were in the hundreds of gigabytes, and then try to promote that as, oh, wow, I'm using MapReduce. I'm using Hadoop, this new technology that's the big hit for big data. I don't consider hundreds of megabytes big data. And in fact, Excel is faster at that sort of analysis than Hadoop was. And this is largely because of that overhead. There's a lot of I/O that has to happen with something like MapReduce. You break the job up, map it over the multiple servers, send it out to them, gather the results back and reduce them and return the results. That is a lot of overhead that has to take place if you do this entirely in a distributed system. So we're looking at how can we combine these two together? How can we combine these two together and take advantage of the overlap in that Venn diagram? And that overlap here is called HTAP, or Hybrid Transactional Analytical Processing. This is about using the same system to both run your ACID-compliant transactions, have as your system of record for your data, as well as run your analytics, and then use the results of those analytics to inform future transactional activities. So ACID-compliant transactions plus powerful analytics equals better real-time decisions. That's the goal. I mean, the goal in the end, I'm an engineer, but the goal in the end for these things and why you're building them is to answer business questions and improve your systems. So you want to take your transactional data that you're collecting from your customers, from your users, from your systems, and you want to store that in Neo4j, run your analytics on it, and feed the results of those analytics back into your transactions, in addition to possibly doing reports and other things. But it's really about how do we do this online? How do we provide better quality applications by using the data that we have in our system? Now, why Neo4j for analytics? This stuff is all evolving, but right now what we have here is the Neo4j native graph database. You're storing your data in nodes and relationships. Think of relationship first paradigm here. If you go down the left-hand side, we already have integrations with a variety of different analytical tools. So I talked to you about how you could use iGraph with Neo4j using the R library, or you could use Spark with Neo4j using Apache, the OpenCipher CAPS project, as well as some of the open source projects like Maze Runner. And I talked about how you can use Gephi and desktop tools. So all sorts of different analytic integrations. We're going to talk the rest of the presentation largely about the optimized graph algorithms on the bottom left, So we'll explain that more here shortly. And then there's a wide range of APOC procedures. APOC stands for Awesome Procedures on Cipher, and is basically a library of hundreds of stored procedures and functions that make it easier to pull data in and out of various data sources, aggregate data, clean it up, et cetera. And the Cipher query language ties it all together. You're using the Cipher query language to access your data, pull out the relevant subgraphs, pass them to the analytical functions, and gather the results. So let's dive into the algorithms part. Now, you probably have already seen this, but we have 3 different types of algorithms: pathfinding, centrality, and community detection. Those are the groups that we put them in. These form a variety of functions across many disciplines. So I'm going to highlight some of that here. Is, one of the things, these are known as social network analysis. These are known as tools which are useful for analyzing how people interact with each other, but that's actually not its only use. Google demonstrated this, obviously, by creating PageRank, and they've built billions of dollars in value off of the concept that these types of analytics can be used in a variety of different businesses. Right now, if you search graph algorithms on the web, well, maybe after this talk, it'll say Ryan Boyd at the top there, Neo4j. But no, right now, if you search graph algorithms on the web, you get basically academic articles. You get computer scientists in academic organizations looking at these graph algorithms. There's a wide variety of other uses of this. So I'm going to highlight a few. I think we just released a white paper, and we're working on a book that covers these things as well, to really let the world know how these graph algorithms can be used for other purposes, for other types of businesses. Were any of you at Graph Connect New York? Okay, a handful. I gave a demo in the keynote at Graph Connect New York about anti-money laundering use case. And one of the things that, so my job as an engineer, I'm kind of in the marketing group, but the idea behind that is that I still have that engineering component in me. I don't want to ever talk about things which aren't real or I haven't seen. And so I was trying to come up with the demo for Graph Connect, and I really wanted to find, I had a hypothesis that this would be a good use case, but I really wanted to find solid evidence of it. And this is actually a paper that was put together by the Federal Reserve talking about how they use graph algorithms and apply it to detecting money laundering in the US. So, all the bank transactions over $10,000, I think it is, need to be reported to the government. And they use graph algorithms for that analysis. There are also plenty of usages across product recommendations. And this is the Neo4j sandbox for product recommendations, which you can step-by-step go through a variety of different ways that you can apply graph algorithms to building better recommendations. And hopefully the recommendation engines that you guys build don't recommend these types of products to me. I really didn't understand this. So I think, at one point I had bought shelves from my garage, but apparently buying shelves from my garage means that I'm interested in material handling supplies. And the only use that I could think of of any of these objects was that flammable keep away box to kind of store my MacBook Pro in when I'm not using it. But otherwise, why material handling supplies? So anyway, hopefully you build recommendation algorithms that look something better than this. Speaking of recommendations algorithms, how do we figure out the top tennis players in sports? Top tennis players in sports. Top sports players in tennis. As you can see, I'm not much of a sports person. But the NIH, the National Institutes of Health, actually published a paper on doing this, using the PageRank algorithm to determine the top tennis players based off of, what is the ladder that passes through, the different matches. And urban planning is also a way that graph algorithms are used. And this kind of speaks to me. My last job was actually in doing architectural software. And there was an engineer in our team that did a lot of this predicting human movement on corporate campuses. So how do we make sure that our employees are more efficient as they travel around the campus? And he basically figured out this calculation for a company and said, you are going to save millions and millions of dollars if you just put an exit here and an exit over here, or an entrance over here, because people are often going right here, but they end up going all the way around because of the way that the landscaping was designed. Well, the company actually decided they'd rather have the employees experience the landscaping and get a little piece than have the most efficient route. But in urban planning, in larger cities, looking at how the foot traffic moves, looking at where we should locate city utilities, maybe cities that have bathrooms, public bathrooms, unlike San Francisco, might want to know where those are. Or you might want to know where to put parking garages, gas stations, stores, and things like that. So how do you look at this using the graph concepts in order to determine the most optimal city designs? Nuclear waste cleanup, this kind of caught me by surprise, actually. The human brain is basically a bunch of nodes and relationships. Well, chemistry is a bunch of nodes and relationships. You have things that bond with other things, forming a relationship. And apparently, you can isolate the water molecules, or isolate the nuclear waste from water molecules, and using PageRank, and use that to inform how to clean up the water, removing that nuclear waste from that water. So the chemical bonds here are really relationships in the same way as the relationships we store in a graph. Another thing that graphs often get used for is in criminal investigations. So looking at how people acted together, colluded, or racketeering type cases, things like that. Where are the different money sources, where are the different addresses where people have lived, and the kind of poll data, people, object, location, and events. There's also been some analysis looking at terrorist networks. In this case, this is a graph of the 9/11 hijackers. Unfortunately, for some of these things, they kind of violate what the traditional laws we think of in terms of relationships in a graph. Some of the strongest relationships in this graph were formed years earlier, and the people didn't talk to each other for years. Or they only activated that relationship every now and then. So there's still open questions as to how well this can be used in advance to predict this type of activity, but it certainly can be used to analyze and prosecute the activity. So let's talk about how they work. The developer surface of Neo4j. So who wants to tell me why Neo4j has the 4j at the end of it? Anyone? Java? Yes. So back many, many years ago, there was log4j and a variety of other Java projects, Java libraries had 4j in the name. And that's where Neo4j originally came from. Since then, we've grown up a lot. So we originally were this embedded Java API. And now many of the people that use Neo4j don't even use Java in their environment at all. Because we went to more of the client-server model. And we haven't changed the name because the name's kind of cool. But we went to the client-server model in the first couple steps there. And it was originally with HTTP-based protocols. Then we went to a binary protocol to make sure that the type safety existed. So for those of you who worked a lot with JavaScript and JSON, you have very little type safety as you transmit that data. But Bolt allows us to have a binary protocol and a binary format for our data to get that type safety. We also released a variety of language drivers. But an important thing we did in 3.0 and 3.1 is release these user-defined procedures and functions. And then in 3.2, the user-defined aggregation functions. This allows us to run code inside the JVM, inside the database, that allows us to do some of these more optimizations that we've been talking about. And so this is an important extensibility point for those of you who are not Java developers. You can write code in a variety of other JVM languages, but it's not sort of done very often. Most people are writing Java if they're writing these procedures and functions. But I will say that a lot of these procedures and functions have already been written for you through the APOC library and through the algorithms library that I'm going to be talking about. User-defined procedures, callable procedures that are callable standalone, but also inside Cypher statements. So what's that mean? Well, here's an example statement that you would pass in Cypher. So you can pass this statement just as you would pass your match clause, and it can be done using any of the standard drivers across a wide variety of different languages. In this case, we're just passing in, we're making up a procedure called search in the namespace example and passing in that we want to search users and for a name pattern here. And this just gets implemented in a handful of lines of code. And in this case here, we're basically just looking at an index and returning the nodes that are in that index. But you can see that basically what is a user-defined procedure is just implemented as standard Java code with the methods annotated with procedure and some of more information. Instance, it's saying here that the mode is read. So this procedure we're saying only has access to read data. You can also write data, but the engine needs to know which mode you want. And it's really easy to write these procedures. You just build them into a jar file, throw it in your plugins directory, and they're there. So this is just kind of describing the data model that we hand back, search it. And then we're talking about here how you actually call that procedure. So this is using the Java driver again. You could use any of the drivers, Python, JavaScript, .NET, and then any of the community drivers, PHP, et cetera. And you're literally just passing in your Cypher statement saying to call that procedure. So it's pretty simple. And you're not here to learn how to write procedures, but I just wanted to give you the basis of how these algorithms are built. They are all open source. You can check them out on GitHub and read how these procedures are written. We have a team of people who have been working night and day to optimize these. And we're really trying to make sort of the best graph algorithm implementations. Obviously, the algorithms themselves are fairly standard in most cases, but we want to make it as efficient as possible to run inside the database. So I'm going to go through some demos here of various procedures, but I do want to point out that you can go to neo4jsandbox.com and you can launch the Graph Algorithms Sandbox. You just have to sign in with a social account or make up a password, and then you can launch this Graph Algorithms Sandbox. And basically what that gives you is an instance of Neo4j running under Docker, running on AWS, that we foot the bill for a couple days, and it allows you to run these algorithms on smaller size data. We don't give these things that much RAM, but you can run algorithms here, and it gives you a guide that steps through a data set and steps through, this is basically a Game of Thrones data set and showing about the interactions of the characters in Game of Thrones. And it steps through that with a guide that shows you each of the Cypher calls that we're making to these various procedures and what those procedures do, and educates you on that. There are also a handful of other sandboxes the Russian Twitter troll sandbox, the Legisgraph sandbox, and then the recommendations engines that all include algorithms and how those algorithms would apply to those different data sets. Of course, if you're using Neo4j Desktop, we actually have the ability now that you can install the Graph Algorithms plugin directly from Neo4j Desktop by just clicking that button down there, and it will install it in the database in your current project. So how are the algorithms used? As I mentioned before, you're calling it as a cipher procedure. You're passing in basically what is the required information for that particular algorithm, which are things like what labels you're trying to run it across or the properties, et cetera. And then there's two different types of result sets that you can get back. Either you can stream the results back, making no write transactions to the database, or you can write the results back to the graph to then inform future analytics that you run, future transactions that you run through the database, as well as possibly be a feeder through to other algorithms that you might apply on top of those results. You can do this thing called a cipher projection. So oftentimes your graph may be further complicated or more complicated than what the algorithm typically would expect. So for instance, if you have intermediate nodes in your graph and you want to collapse those to remove the intermediate nodes when you're running the algorithms, you can pass in a cipher statement that is essentially a view or projection on top of the graph for the algorithms to run on. So let's do some simple ones here. This first one is all pairs shortest path. How do we figure out all of the shortest paths here between each pair of nodes? This might be something that is used in urban planning to figure out the ways to get from A to B across the whole city and what might be on those paths. Some of these algorithms are assuming something, I should say, in terms of human psychology, that we do want to always take the shortest path. It's not always true. At times, like I mentioned, that corporate example of a corporate campus, at times you're going to want to actually take the more scenic path rather than the shortest path. But if you assume everyone takes the shortest path, what path would they take? And then we have a cipher query here that the first line actually calls the all shortest path procedure and says to stream the results back. It says what it's yielding as the results of that procedure, and a few more things here. And then after we get those results, we're passing those results through with some match statements and then doing a return. So oftentimes when you get the results of the algorithms, you're going to do some further filtering or sorting or things like that using standard cipher queries. And you get something like this. So you basically are saying if we're trying to go from A to F, the cost of that is 100, and that's the sum of the cost weights that are on each of the paths between A and F, and similarly for the other pairs. PageRank, here's a very simple graph here of what a web layout might be for a site. So we have our home page, we have a product page, we have an about page, and then we have a page of links. So if that is our company's website or our personal website, and then we have various other sites that we link to and in this, and we can see then what the PageRank result is. And for those of you who are not familiar with PageRank, basically what happens is that incoming traffic awards you a set of points, and then your outgoing traffic from a particular page here, outgoing links from a page, divides up some portion of the points that you have received by people linking to you. And so it's very simple here. In this case, we're just looking for the PageRank. We're not trying to do any further processing or sorting. PageRank requires a number of iterations and then a damping factor. You can read more about that, but this gets you the basic result of a PageRank. and shows us what we would expect for that graph, which is that the home page, where all of the other pages on the site link to, has the highest page rank. And then some of the other pages which are linked to from the various other sites have some higher page rank. It's a very simplistic example, but sometimes the simple examples help you understand it more. If you look in the recommendations guide or recommendations sandbox, or actually I think all of those sandboxes that I mentioned earlier do have more complex examples of PageRank. Now you can get complex also with the size of the data. And so here's a result doing PageRank on the Wikimedia or data set, the Wikipedia subset of the Wikimedia data set. And we can see here the page there with the highest page rank is United States. I imagine that's because there's a lot of geographic territories, different states, cities, et cetera. And Wikipedia tends to be very US-centric. Betweenness centrality. How do we figure out kind of who the influencers are in this network? This can be used for organizational behavior. How do we understand if we are trying to influence a population within an organization, who do we connect with to influence that? So this is actually just a very simple graph here of different people and who they manage, so an organizational hierarchy. And we want to say, call the betweenness algorithm on all the users, on the manage relationship, and then the direction of the relationship. And in this case here, then we're trying to return the list of users and their centrality score. And here we can see Alice wins this match because Alice is able to influence a lot of people in this network. So her centrality weight is 4, and that just means that she can be influential. The LegisGraph network is a really fun one to do this with. The LegisGraph sandbox has basically, I don't think it's the current Congress, but last year's Congress. It has all of the bills and congressional representatives and what the votes were, what the sponsorships were, and things like that. That's a fun one to do some of the betweenness centrality on to figure out who is influential in Congress. Closeness centrality is basically what is the node that has the shortest distance to all other nodes. So you might do this in a transportation grid or something like that. So very simple call as we did before. And the results here are kind of as you would expect. So C is basically the node that is able to connect at shortest distance to all of the other nodes. Obviously, as the graph gets more complex, you can't just look at the graph and know this answer, but that's a pretty simple illustration of what this algorithm does. Strongly connected components. What are the clusters in the graph? What are the groups of things which interact heavily with each other in the graph? Who are the cliques? And you can analyze this on this very simple graph of follower relationships. So if you think about something like a Twitter graph where you can follow unidirectionally and sometimes bidirectionally. And so we're going to run the strongly connected components on this and get the results here. And you can see basically what we've done is partitioned or clustered different parts of the graph. So we have Alice and Bridget and Michael in the same partition, Doug and Mark in a different partition. And you can see when we bring back to the larger graph, Alice, Bridget, and Michael are the ones that are heavily connected with each other, and Mark and Doug. Now, this is a lot better way to view it. So in this case, using color to indicate the different clusters. If you look back at the Graph Connect keynote from last year in the anti-money laundering example, we do a similar thing in a different visualization tool, showing you visually how the clusters work. Speaking of visuals, so what are the different types of ways that we can visualize the results of our algorithms? Well, we can impact the size of the nodes, the color of the nodes, the placement of the nodes visually in the graph in the two-dimensional space, and then the thickness of relationships. So let's look at something like this. And this is the Game of Thrones data. And we are looking at a graph that uses all of those different aspects. The thickness of the relationships indicate the strength of those relationships. And then we're using size and color as well. And you can see here in this code how we are doing each of those things. So this code is, well, what we're showing you is a configuration for a thing called neoviz.js, which is a library we just started talking about, built by Will Lyon on my team. And Will did an excellent 8-minute screencast on this that you should all check out. It's on the homepage of our YouTube channel, which you subscribe to as well. It is literally one of the best screencasts I've seen, and I've done a lot myself. But this is Neoviz. Neoviz is built on top of a thing called viz.js. And basically, it's how do we make it super easy for people who are using Neo4j to visualize the results of their graph programmatically. And we see here, in this case, we're specifying the different labels that we're using for the different node types. So in this case, the label is character. And we're saying, here's how to caption the character nodes. Here's what the size should be based off. In this case, base the size off of the page rank of the individual character. And then what community they are. So we've pre-computed the community in the graph using one of those community detection algorithms. And we're using that. And this should kind of say color, basically, is determined based off the community. And then on the relationships, we're saying that the thickness is based off of the weight property, which has been determined algorithmically as well. And so if we look back here, so we had the size of the nodes based off the page rank, the thickness based off of that weight property, the colors based off the community, and all of a sudden we can see a lot more just looking at this graph. We can see, hey, this node has the highest page rank. We can see that probably purple here, I think, has a lot of really strong relationships. Actually, this purple or this pink has really strong relationships as well. And then we can see the different clusters of characters and how they interact with each other. And what if we add the third dimension? I just want to mention this as a future type thing. There's a company, Kineviz, for those of you who were at Graph Connect. Kineviz did a 3D graph visualization in VR. You can strap a headset on and walk through the graph. The company is doing more and more of this 3D graph visualization and trying to allow business users and educational users to understand graphs better by looking at it in 3D. And obviously, this is only a 2D representation. But the 3D representation, if you have that headset on, gives you another layer to work with when you're looking at graphs. You know, beyond just color and size of nodes and thickness of relationships, you also have the 3D layout to look at. So about wrapped up here, but I do want to say we do have a survey right now for Neo4j users. It's not related to this particular event, but in general for Neo4j at bit.ly/neo4j-survey. And this will give you a $10 discount code to our Graph Gear store, which you can all look at various swag items. And if you think you're doing something awesome in the Neo4j community, whether it's writing blog posts or code or doing meetups or things like that and deserve free swag, feel free to reach out to us and we can look at giving you free swag as well. But we wanted to create this so anyone could get the swag that they wanted. So fill out that survey at bit.ly/neo4j-survey and you get your swag at graphgearstore.com. And that's all I have.